use Green's theorem to calculate the line integral over the curve C of the function sine parentheses x squared close parentheses dx plus open parentheses 3x minus y close parentheses dy, where C is a right triangle with vertices 3 points, -1, 2, the point 4, 2, and the point 4, 5 oriented counterclockwise. Now, Green's theorem says that we can turn this line integral into the double integral over a region D with respect to A of the function qx minus py. Now in this case, our p is sine parentheses x squared close parentheses, and our q is parentheses 3x minus y close parentheses. So we'll take those partials first off. So here qx would be equal to 3, and p sub y would be equal to 0. So this is going to become integral over the region D with respect to A of 3 minus 0, or 3. So in order to find this line integral, we need to figure out what the regions, the boundaries on the region D is going to be. Well, imagine what those points look like. In fact, I will draw those points on a coordinate axis. So the point -1, 2, the point 4, 2, and the point 4, 5. Those, of course, form a right triangle. It's up to us to figure out what the boundaries are. Well, I'm going to go ahead and say the boundaries on x are from -1 to 4. So x is the boundaries -1 to 4. But that makes y, that boundary, is a function of x. And so if we find the slope and the y-intercept for the line connecting the points -1, 2 and the point 4, 5, we see that these boundaries go from 2, the lower boundary, up to 3/5 x plus 13/5, writing that in terms of x. So our double integral over the region D with respect to A of 3 is going to be equal to the integral from -1 to 4 with respect to x of the integral from 2 to 3/5 x plus 13/5 with respect to y of the function 3. Now, because this is a constant, this actually is equal to 3 times the area of the triangle. And it turns out that the area of that triangle is, well, it has a base of 5 and a height of 3, so that's going to be 15 over 2, so that this total line integral value is 45 over 2.